Welcome to our lectures on flexible ST transmission system. Today we shall continue with the UPFC. So, we have started discussion on previous class on the control structure. Let us continue with it, and we have already told that with the suitable control, the UPFC can cause series injected voltage vector to vary rapidly and continuously in magnitude and angle as desired. So, it can control by series injections, and voltage and angle it can manipulate by the voltage source converter, and accordingly it can change magnitude as well as the phase as desired. So, due to this so it can inject both in phase, both in actually not only quadrature and phase, in any magnitude and the any angle, and thus we have a considerable advantage of UPFC. It is not only able to establish an operating point within the wide range of possible P and Q condition on the line, but also it has the inherent capability of transition rapidly from one such achievable operating state to the another such operating state. So, if you wish to change of power in the transmission line from the point P1 to P2, this device can ensure that it reaches the point in a fastest possible way. So, you can have we have discussed the series, different kind of series compensations. There you cannot independently control P and Q. Here there is a big advantage, you can shift the operating point from one P and Q point to another P and Q point, and that transmission can be very fast. The control of the UPFC is based upon the vector control approach, that is since we have take the magnitude and the phase of the voltage while injecting a particular voltage, for this reason we call it is a vector control approach. The term vector is used instead of the phasor in this section to represent the set of instantaneous phase variable. These are voltage, current, and whose total sum is actually 0 for balanced 3 phase 3 wire system. And the symbols, this V delta and the I delta, are used for the voltage and current vectors. You may actually say that it is a contradicting with fundamental quantities, because potential, essentially the voltage is a scalar quantity, but it has an advantage of using a vector quantity because it will be represented by the phase and its magnitude. So, you can treat them as a vector quantity for sake of understanding it. These vectors are not stationary and are rotating, but moves around the fixed point in the plane as the values of the phase variable changes, describing desired trajectories, which because actually circles. If we shall plot the P and Q, and we will see that actually the locus of control of those UPFC, and the trajectory can be any conic section, ellipse, circle, and we will see that how it will be generated in few minutes, identical to this obtained in the phasor, when the phase variable is represented by a balanced steady state condition. These vectors are an orthogonal coordinate system with P and Q axes such that the P axis is always coincide with the instantaneous voltage vector V, and the Q axis with the quadrature with it. In this component, in this case coordinate system, the P axis current component is actually the in phase component, that is IP, accounts for the instantaneous real power, and Q axis current component IQ for this reactive power. Under balanced steady state condition, p axis and the q axis component of the voltage and current vector are a constant quantity. So, that is thus actually the amount of the p and q, the reactive power and the real power required to be constant. These characteristics of the described vector representations makes it highly suitable for the control of UPFC by facilitating the decoupled control of real and the imaginary power. So, we shall separate control on PQ in real and the imaginary. Thus, we shall establish the network. The UPQC control system may be divided functionally into internal or the converter control and the functional operational control. The internal control operates the two converters so as to produce the commanded series injected by the voltage, simultaneously draw the desired shunt current. The internal control providing gating signal to the inverter valve, so that the converter output voltage will be properly respond to the internal reference variables such as IPRF, IQRF and VQRF. This series converter responds directly and indirectly to the demand for the series voltage vector injection. Shunt converter operates under a closed loop current control structure, whereby the shunt, real and reactive power components are independently controlled. So, what else? The shunt real power is dictated by another control loop that acts to maintains to preset the voltage level of the DC link, thereby providing the real power supply or the sink needed to support the series voltage injection. So, we have another loop. That means, the control loop for the shunt real power ensures the required real power balance between the two converters. As mentioned in case of UPFC QC, so it is same for the UPFC previously, the converter does not and exchange the reactive power through the link. The external or the operational functions of the control defines the functionally operating mode of the UPFC and is responsible for generating the internal references. So, this is the actually the control. So, you have a series and you got a shunt converter, you will sense SH and V1 and actually you will sense the V reference. From these things actually you have actually V reference here and you sense the actual VDC, and thus you maintain the DC link voltage. Maintenance of the DC link voltage is a task of the shunt filter, and also you got IQ rev, so that it will inject the IQ rev and make the current in phase with the voltage, and this will be actually the voltage V1 and V2, and you have a VQ ref to have a desired power flow from this UPFC. So, for this reason it will inject the PQ in some phase and magnitude, so that you send a here sending P1 and P2. So, here it will be changed to desired P and Q. The functional operating mode and the compensation demands represented by external reference input can be set manually by the operator or dictated by the automatic system optimization control. Either it will be sent by the users or this is the power demand, or you require to optimize your network, cost optimization or the efficiency optimization or loss optimizations. Control made to specific operating and the contingency requirement. The capability of unrestricted series voltage injections through independently controllable reactive power exchange offered by the circuit structures of two back-to-back converter facilitates several operating and control mode for the UPFC. These include the option of the reactive shunt compensation and the free control series voltage injection according to a prescribed functional approach selected for the power flow control. So, this is the overall structures of the UPFC that we have discussed already. Essentially, this is a shunt compensations. So, you have actually reference of ISH that require to be injected, and you require to maintain the DC bus voltage, and you have a operator inputs and the power system variables, and they will feed the data of V1 reference, ISH reference, that is VQ, that is injected voltage reference, that is impedance reference, conductance reference, power reference, or the reactive power reference, and these are the actual values required to be sensed. You require to sense at least two current or three phase three wire system. Mostly our transmission lines are three phase three wire. So, it will be ISH and the VDC, and thereafter you will have to sense the current I at this point as well as the two voltages V1 and V2, assuming that it is a three phase three wire system. So, from there actually we have a phase lock loop that will generate the actually the theta, and ultimately it will be converted to the actually ABC to DQ frame, so that it can be totally decoupled, and thus the control reference will generate a different kind of getting signals, and that will be fed to the shunt converter, so that actually it sinks or provides the current ISH at the constant voltage of V1. And similarly, the PQ reference which has been calculated, it will be injected here in series, so that you can transmit desired level of P and Q to the system. So, from this understanding, we can say that shunt converter is operating so as to draw a controlled ISH from the line. It has a two component mainly, it is mainly makes mainly actually is a reactive power component of the current that is been provided. The component of this current ISH is automatically determined by the requirement of the balanced real power of the series converter. The other current ISHQ is the reactive component of the load current. Reactive component and can be set to any desired reference level, inductive or capacitive, within the capability of the converter. The reactive compensation control modes of the shunt converter are very similar to those commonly employed for the STATCOM and the conventional static var compensator. And let us see how it will control the P and Q. So, that is actually reactive, this is actually Q control, similarly we have P control. In this mode, the reference input is an inductive or the capacitive var requests, mostly it is inductive. The shunt converter controls translate the var reference into a corresponding shunt current requests and adjust the gating converter to establish the desired current. The control in a closed loop arrangement uses current feedback, signals obtained from the output currents of the shunt converter to enforce the current reference. The feedback signal representing the DC bus voltage VDC is also used to ensure necessary deceiling voltage. Now, we have a voltage mode control. We generally correct the SAC in case of the voltage mode control. Let us see. The voltage mode control, which is normally used in all practical applications, shunt converter reactive current is automatically regulated to maintain the transmission line voltage reference. So, it will inject the reactive power value at a point of the connections or point of common coupling, generally we say, with a definite droop characteristics. The droop factor defines the per unit voltage error, per unit voltage error per unit of the converter reactive current within the current range of the converter. Voltage control uses voltage feedback signals, usually representing the magnitude of the positive sequence component of the bus voltage V1. This series converter controls the magnitude and the angle vector VQ injected in series with the line. The voltage injection is directly or indirectly always intended to influence the flow of the power on the line. VQ is dependent on the operating mode selected for the UPFC control flow. The direct voltage control mode, there is a one case that is called direct voltage control mode. Series converter simply generate the voltage vector, that is PQ, with the magnitude and the phase angle requested by the reference input. The operating mode may be advantageous when the separate system optimization control coordinates with the operations with the UPFC and other fax controllers employed in the transmission system. Special functional cases of direct voltage injections include those having dedicated control objectives. When the injected voltage vector PQ is kept in phase with the system voltage for the voltage magnitude control or in quadrature with the controlled quadrature boosting or the quadrature with the line current vector to provide controllable reactive power compensation. Bus voltage regulation control mode. The injected voltage vector PQ is kept in phase with the input bus voltage vector V1 and its magnitude is controlled to maintain the magnitude output, but voltage vector V2 at the given reference value. Line impedance compensation mode. The magnitude of the injected voltage vector VQ is controlled in proportional to the magnitude of the line current I, so that the series insertion emulates an impedance when viewed from the line. The desired impedance is specified by the input in general. It may be a complex impedance with resistive and the resistive and the reactive component of either polarity. The special case of the impedance compensation occurs when injected voltage is kept in quadrature with respect to the line current to emulate purely reactive, that is capacitive on the inductive compensation. This operating mode may be selected to match the existing series capacitive and the line compensation of the system mode. So, both can be coupled together. Another is actually the phase angle regulation mode. You can this UPFC can act as a PAR. So, injected voltage, the PQ, is controlled with respect to the input bus vector V1, so that the bus voltage V1 is phase shifted without any change in magnitude relative to V1 by an angle specified by the reference input. One special case of the phase shifting occurs when PQ is kept in quadrature with V1 to emulate the quadrature booster, that we have already discussed in case of the series compensation. Now, this is the power flow control. We want that actually amount of the power flow through the line can be controlled by the UPFC. Thus, it is automatic power flow control mode. The magnitude and the angle injected by the voltage vector PQ is controlled. So, control has to force that the line current vector I result in the desired real and the reactive power flow through the UPFC. In automatic power flow control mode, the series injected voltage is determined automatically and continuously by a closed loop control system to ensure that the desired PQ are maintained despite power system changes. That is something we require to do. The operating mode, which is not achievable with conventional line compensating equipments, has far reaching possibilities for power flow scheduling and management, because it can dynamically control the flow of the power into the system. It can be applied effectively to handle dynamic system disturbances and dynamically tamp out the oscillations and the transient stability. So, these are the cases it is found to be very suitable. Now, so let us discuss the basic control systems for the PQ control, how you do it. We shall first discuss it, thereafter we will show you the control technique. The UPFC has many operating mode that we have already mentioned. So, but only automatic power flow mode of control providing independently control of real and the reactive power flow in the line. So, independently you can control P and Q. This control mode utilizes most of the unique capabilities of the UPFC, and it is expected to be used as a basic mode of the majority of the practical applications, such that shunt compensation is used normally for the automatic voltage control. Accordingly, we shall show the block diagram having a greater details of the control schemes are shown in the series converter and the shunt converter. The control scheme shown assume that the series converter can generate the output voltage with controllable magnitude and the phase angle given by the DC bus voltage. So, this is the control PQ control. So, you have either you have a automatic control or the customers or the administrator will actually set these things. These are V1, P reference and the Q reference, and thus you will sense that actually the sending end voltage V2. And so, there is a block will be calculating IP star, that is IP reference and the IQ reference, and you have actual values of I and V, V2. From there you can calculate the actual value of P and PQ. So, you will be mostly it is generally done by the PLL and make it a DC quantity, thus actually P become D and Q generally written as a Q as a nomenclature. So, now it will be fed to the error amplifier. Error amplifier is essentially an PI controller or PID controller in most of the applications. So, there will be a voltage limiter because error can go very high and low. So, you have to truncate the error, and it will take these inputs also from the sensors. There is sending end voltage, actual receiving end voltage, and I. So, these are the, based on that these two calculations will be made and will compare, and from there actually it will estimate the value of the Vp and Vq of required to be injected by the series injector. And you will have a phase lock loop, you can have a phase lock loop to be fitted here also, and then it will become all is operating in a DQ mode. Otherwise, it can go like this. Magnitude and the phase angle of the computer, basically it will check the magnitude V Q and the Vp, and angle and tan phi will be basically, tan rho will be basically Pq by Vp, and you will add the phase with it, or then you have to convert it into the, and thus you get a Pq with an angle to be injected, that is theta plus rho. So, this voltage will be injected by your series regulator. This is the control of your automatic power flow control. So, the control schemes for the shunt active power filter assume that the converter can generate output voltage with controllable magnitude and angle. However, this is not always the case, since the converter losses and the harmonic can reduce the allowing the DC level voltage, DC link voltage to vary according to the prevailing the shunt compensation demand. So, we have to actively compensate the DC link voltage. Although the variations of the DC link voltage inevitably reduce the attainable magnitude of the injected series voltage when the shunt converter is operated with high reactive power absorption. In many applications, this may be acceptable trade off. So, we have to set a limit on it. So, this is the actually the basic control of the PQ, and this is the sense voltage V1 of the sending end voltage and the voltage magnitude, and you will have a Vref. So, from there you got a error of the PI controller, and you have to maintain the DC link voltage. So, this is VDC ref minus VDC minus. So, you got an error amplifier, and this is for to meet the losses due to harmonics and the switches, and this will be the reactive power, and ultimately this value will be the ISHQ. This is the shunt part of the system, and thus you compute the ISH, that reactive power component of the computer, assuming that we have predominantly reactive power. So, you have ISHP and ISHQ. So, this ISHP in phase component will be added with the loss component of it. So, ultimately it will give you ISHP, and both will be fed to the error amplifier, and from there we will compute the magnitude of it, and you have a phase lock loop. From phase lock loop we will compute theta and this alpha, then this theta and alpha will be added to give the desired the phase shift, and ultimately this current will be converted to the equivalent voltage of VSHs, and you will be fit that logics into the converter to compensate for the shunt compensation. Thank you for your attention. I will continue to your next lecture with UPFC.